This is a high-visibility, multi-million-dollar software rollout, planned to the minute. Every single milestone is color-coded green. The team consists of 12 developers, 4 QA leads, and 2 business analysts. Every task is sequenced into a timeline designed for maximum efficiency. This Gantt chart shows the strategy. Every team member is stacked at 95 to 110% capacity. The logic assumes that filling every available hour on the calendar will result in the highest possible productivity. On paper, this math secured stakeholder approval. In reality, it created an invisible and unsustainable workload. The first sign of trouble arrived at 11:47 p.m. on a Thursday. The team's strongest back-end engineer sent a message stating she was simply running on empty. Over the next 3 weeks, the project began to unravel. 2 developers started applying elsewhere, and a senior QA lead was forced onto medical leave. This graph shows the resulting collapse in sprint velocity, the measure of a team's actual output. In just 14 days, the team's capacity fell from 94 story points to just 41 points. This data shows the core failure. When teams are forced to sustain 100% utilization, they don't produce more. Their productivity actually drops by 53%. The schedule didn't break. The people carrying the schedule broke. Optimizing for time while ignoring human capacity eventually causes the system to fail. The crash was caused by a common error, treating mathematical allocation on a spreadsheet as if it were true human capacity. An 8-hour workday rarely produces 8 hours of work. Constant context switching, administrative tasks, and the need for mental recovery between complex problems reduce the actual output. This diagram shows the erosion of a standard day. After accounting for meetings and administrative recovery, only about 5 or 6 hours remain for deep work. Sustainable scheduling requires a baseline of roughly 70 to 75. To protect the most critical parts of the project, managers must ring-fence their lead engineers, blocking their calendars to shield them from minor, non-critical interruptions. Protecting these experts from administrative noise is the only way to ensure the project's critical path stays on track. Most projects use a single contingency reserve at the very end of the timeline. A more effective approach uses task-level micro-buffers to protect resources in real time. This chart shows the trigger. When an individual's utilization exceeds 85% for 2 consecutive weeks, the system automatically appends a buffer day to their tasks. Project leaders must also identify single resource dependencies, those moments where only one person has the knowledge to complete a critical task. Cross-training staff to eliminate these dependencies takes a few hours up front, but it prevents the weeks of delay that occur when a single expert becomes unavailable. The final optimization tool in this framework is the establishment of psychological safety. When managers create a safe channel for teams to flag capacity concerns, they can intercept problems early. It shifts the culture from one that hides burnout to one that addresses it. This data shows the payoff after 18 months of tracking. Using proactive resource leveling resulted in delivery speeds 2.8 times faster than traditional methods. At the same time, the team retention rate stabilized at 94%, keeping the most experienced engineers on the project. A schedule that looks ambitious to stakeholders but is impossible for a team to survive is not a plan. It is a promise already broken. Success requires moving past spreadsheet optimization and starting to manage the people who carry the schedule.